Hello everyone! Today we will talk about the regional wind patterns. This video is presented by Miss Jasmine S. Laron and Miss Regine Mizate Tinkang, BSc Science 3 students of Bukidnon State University. The learning objectives of this lesson are: understand the concept of regional wind patterns, identify the driving forces of the regional wind pattern, and explain how these forces influence the wind direction. Let's get started! There are four forces driving the regional wind patterns: the pressure gradient force, or the PGF, which is due to regional differences in air pressure; the Coriolis force, which is due to the Earth's eastward rotation; the frictional force at the surface where wind and land meet; and the centripetal force associated with rotation of air masses. Now let's further discuss each one of them, and let's begin with the pressure gradient force. A pressure gradient is simply differences in pressure over distance, and it is differences in pressure that leads the pressure gradient force, which has now become one of the fundamental driving force of the regional wind pattern. To further understand how the pressure gradient force really works, we need to know that PGF naturally flows from area of higher pressure to areas of lower pressure. To illustrate this, let us suppose that point A has a pressure of 1013 millibars and point B has a pressure of 997 millibars. Well, because the pressure are different, air will naturally flow from point A, the area of higher pressure, to point B, the area of lower pressure. Now, the greater the difference in pressure, the faster the flow of the air will be. In other words, the wind will be higher. In the weather map, we can see the pressure gradients by means of isobars, which are the lines of same pressure. The closer the isobars are to each other, the faster the wind is in the particular area. Without additional forces, all winds would move perpendicular to isobars. Coriolis effect or Coriolis force. This is caused by the rotation of the Earth. The Earth rotates faster around its equator than it does at its poles. This is because points near the equator of the Earth have farther to travel in a day or in a 24-hour period than points closer to the poles. This explains the differences in the rotational speed of the Earth on its equator compared to the poles, and this has an impact on the direction of the wind in the North and South Hemisphere. In the Northern Hemisphere, Earth's rotation is counterclockwise as seen from above the North Pole. In the Southern Hemisphere, the rotation is clockwise as seen from the above of the South Pole. The Coriolis effect causes free-moving objects in the Northern Hemisphere to curve to the right, and free-moving objects in the Southern Hemisphere to curve to the left. Another driving force of the regional wind pattern is the frictional force. Friction only influences the direction of wind when it is close to the Earth's surface, and that is typically defined as less than 700 feet above the surface of the Earth. When the wind is close to the ground, it is affected by the friction of objects and topography of the surface. But once we get over 700 feet above the surface of the Earth, friction will no longer have a measurable impact on the direction of the wind.
The centripetal force is the inward force created by a spinning object, like air around a low or a high. The centripetal force is a real force that directs spinning objects inward. It is often confused with the fictitious centrifugal force that is said to push spinning objects outward. In fact, the centripetal force and the centrifugal force always exactly offsetting, so any problem in physics can be addressed using either